Oh, chemistry goddess, would you like to try some of our lemonade?
We would like to test it to make sure it's hydraulic like you.
Oh, definitely. Good.
Is something wrong?
Yuck! It's disgusting. It's hot. It's so sour. Oh, it's much too acidic. Much too acidic. Definitely not fit for a goddess.
Oh my, okay,
I'll
we'll
come
try.
back in 5 minutes. It better be good, ladies.
Okay, thank you. We'll try
our
to use the
best.
chemistry knowledge that you've blessed us with.
Yeah.
I guess we need to go back to basics.
Let's revisit some key terms. What is an acid? What is a base?
A type of drug or maybe a baseball? I don't think so. An acid is a covalent bond formed by a nonmetal and a nonmetal, and a base is an ionic bond formed by a metal and a nonmetal. Oh, and according to the Lewis definition, a Lewis acid is an electron pair acceptor and a Lewis base is an electron pair donor.
Now that you mentioned Lewis, I remembered something. A conjugate acid is a product remaining after a Lewis base has donated an electron pair, and a conjugate base is a product remaining after a Lewis acid has accepted an electron pair.
And acids and bases vary in strength. A strong acid or a strong base will dissociate 100% when forming an aqueous solution and will therefore make strong electrolytes. A strong acid will have a low pH value and a strong base will have a very high pH value. And weak acids and bases do not ionize 100% in water. They exist primarily in the forms of molecules. So that makes them weak electrolytes.
Aren't there species that are amphiprotic where they can donate an electron pair and also receive electron pairs, where they can act as a Lewis acid and a Lewis base?
Yeah, like water in this example. It's a base in this one and an acid in this one. This also explains why water can auto-ionize.
Oh my god! It's all starting to make sense now!
Look at this chemical equation, but it can also be simplified into this. When water ionizes, hydronium is formed and hydroxide is formed. And the equilibrium, when the opposing forces are balanced, can be written as this equation right here. Guys, I found that the concentration of hydronium ions found experimentally is 1 times 10 to the negative 7. And the concentration of hydroxide ion found experimentally is also 1 times 10 to the negative 7 from savitapaul.com.
Wow! Hey, that's fantastic! Now we can use the concentrations and compare the concentration of hydronium and hydroxide to determine whether a solution is acidic or basic. Then we can find a perfect lemonade for Goddess Savita!
First, need to determine whether the solution is acidic or basic. The best way to determine the acidity of a solution is by using the pH scale.
That's the scale that the Danish scientist Søren Sørensen created in 1909.
Because the people of his time had a hard time understanding the negative values of the concentration of the hydronium ion, therefore he used logarithms to simplify these values. pH stands for the power of the hydronium ion concentration. So a change of 1 in pH really means a tenfold change in the hydronium ion concentration.
The pH scale ranges from 1 to 14, 1 being the most acidic and 14 being the most basic. Now let's look at some common household items. Lemon has an acidity pH of 2, so it's acidic. Banana has a pH of 5. Soap has a pH of 10. A drain cleaner has a pH of 14. And finally, water is neutral and thus it has a pH of 7.
So there's also the complementary pOH scale, which is the power of the hydroxide ion. It also ranges from 1 to 14, with 1 being the most basic and 14 being the most acidic.
So let's actually figure out how to calculate the numbers for this.
Well, we know the equilibrium equation for the water ionization is this. But apparently, water's concentration in pure and dilute solutions is constant at 55.5 moles per decimeter cubed. Therefore, we can write the water's constant equation as this. But that's not enough. We still need the pH and the pOH.
Just like any other constant, the water constant is dependent on temperature too. So if we assume that the standard temperature is 25 degrees Celsius, Kw will be 1.0 times 10 to the power of negative 14. And if we substitute this into the original equation and add log to both sides, we will get this equation. And since we know that the concentration of pH plus the concentration of pOH equals 14, this constant Kw will also equal to 14 as well.
That's perfect. So then if we arrange, we know that the hydronium ion concentration equals 10 to the negative pH.
This also works for the calculating of pOH. So pOH is equal to negative log base 10 times the concentration of OH. And if we rearrange this equation, we get the concentration of OH equals 10 to the negative pOH.
And since we already know this equation here, we can arrange it to be able to find the concentration of the hydronium ion and the hydroxide ion.
Example number 1. Calculate the pOH and pH of a solution of the strong base KOH with a concentration of 5.0 times 10 to the negative 3 mole per liter. Let's start off with the equation. KOH separates into K plus and OH minus, and all of them are aqueous. And in the problem they gave us, they told us that the concentration of the KOH is 5.0 times 10 to the negative 3 mole per liter. And since this is a 1-to-1 mole ratio, we know that the OH must also be 5.0 times 10 to the negative 3 mole per liter. And if we know the OH, then we can calculate the pOH, because as we've learned before, pOH equals minus log 10 of concentration of OH. So if we substitute this into this formula, we can get which then equals to 2.30. And if we know pOH, we can also calculate pH, because we know that pOH plus pH equals 14. So if we know pOH, we can subtract 2.30 from 14, which will then give us pH of 11.70. And therefore, our answer for this question is pOH of 2.3 and pH of 11.7.
Example 2. What is the pH of the solution formed when 0.06 moles of NaOH is added to 1 decimeter cubed of 0.05 moles per decimeter cubed of HCl? So first, let's start by writing out the equation for the reaction. Okay, now the first step is to find the number of moles of the hydrochloric acid. So we will do this using the formula N equals C over V. Next, we have to find the limiting reagent using mole-to-mole ratios. So we have to find the ratio of the sodium hydroxide to the hydrochloric acid. So as we can tell, there are less moles of the hydrochloric acid, so hydrochloric acid is the LR, and the sodium hydroxide is in excess. So now we have to find the remaining unreacted moles for NaOH. So we take the moles of sodium hydroxide and subtract the moles of hydrochloric acid. And since there is only one hydroxide ion in the sodium hydroxide molecule, the number of moles in the hydroxide ion is the same as the number of moles for the sodium hydroxide molecule as a whole. So now we need to find the concentration of the hydronium ion, so that way we can calculate our pH. So we're going to use the formula concentration of OH times concentration of H3O plus equals 10 to the negative 14. And then we're going to substitute in our value for the concentration of the OH. So now we need to find the pH. So we're going to use the formula pH equals negative log times the concentration of the hydronium ion. And then we're going to substitute in our concentration. And we'll get our pH value. So we got a pH of 12, which means it's basic. Example number 3. Calculate the pH, the pOH, and the OH concentration of the following solution, 0.002 moles per decimeter cubed of HBr. So first, we're going to write out the equation. Now we will calculate the pH. So we're going to substitute in the value for the hydronium ion concentration into our pH formula. Now that we have the pH, we're going to calculate the pOH using the formula pH plus pOH equals 14. Now we're going to calculate the OH minus concentration. So for this, we're going to use the formula OH concentration equals 10 to the negative pOH. And we already found the pOH before. So we'll substitute that value in, and then it'll give us the OH concentration.
Okay, so after we've done all these calculation problems, I think our main issue with the lemonade was that it was too acidic. Our pH was too low.
Maybe we can add something to neutralize the acidity of this.
Oh, we could use baking soda because baking soda is a base, and in lemons there's citric acid, so the acid and base will neutralize each other.
That's such a good idea. Let's do it.
Oh yeah.
Oh my god!
It looks like lemon meringue pie. I'm not drinking it.
Okay, let me take a sip to see if it's good. This is disgusting!
It's not good?
No!
Oh, I guess we shouldn't have neutralized it completely. I guess it ruins the taste.
Yeah!
Looks like pee.
Someone else drink!
Oh my god, what do we do now?
I have an idea. Miss Poe, we prepared the perfect drink for you.
Oh, what is it?
Lemon tea.
Oh, let me taste it. Mmm.
it
Wow. Perfect, lady.
Really?
What is it?
Lemon tea!
Amazing. Thank you. Thank you. Perfect.
Oh,
Thank you.
yay.
Thank you.